Morning, everybody. Welcome to the final day of lecture in Physics 2B. Yes, yay, right? I mean, I'm getting sadder and sadder because you guys are going to leave me and go on and do your lives and flee the coop. And I always get abandoned, but I understand. It's the way it should be. We have one last chapter to do. We're probably not going to get to all of it because I like to talk about this stuff way too much. But do it we shall, and then we'll have Thanksgiving. When you come back, the Monday that you come back, we are going to, it's going to be just kind of grasp. It's just to kind of, there'll be nothing that will be presented, no new material. If you want to come in and get help to just kind of get all the homework done, turn in your quizzes, it's kind of a day for getting all of that stuff buttoned up. And then the Tuesday we will be reviewing, right? It's the time you come in and just ask me questions. And then we'll take the exam on Thursday. What are we doing finals week? Crying? No, you're just doing the exam autopsy. You can cry about your other classes. But we're just doing the exam autopsy. And I have the date in the calendar that I published on Canvas. Turns out, looks like our exam autopsy is Thursday, December 11th. So because it's on a Thursday, where are we going to be? We're going to be in this room. It's going to be kind of weird, right? Got to do the exam autopsy in this room. So make sure that you get that into your head. You will have to wait a week for your score. You guys are used to getting kind of quick turnaround time on your scores, but that's not going to happen. All right. What's that? The 11th? Yes. Yeah, 8 a.m. So finals week always follows the lecture time. So if your lab-based teacher is giving you a final during a lab, they're doing it wrong. So, which does happen. All right. Chapter 32 is a continuation of 31. We're still talking about nuclear physics. We're talking about radiation, all that kind of stuff. But what we're going to do is we're going to start talking about splitting the atom and putting atoms together. So we'll start with fission, and then we will go to fusion at the very end if there's time. And did you see that I posted the topics for the exam? Okay. So from this chapter, it's going to be mostly the nuclear reactor stuff. So pay attention there. But typically, like, feedback I've gotten from chapter 32 is, Mr. Balogh, why didn't we do that all semester? Because, like, there's really interesting stuff going on in this chapter. And we'll see. We'll get there. We'll see if we can answer some of your questions and all that kind of stuff. Heavy atoms like uranium, plutonium, those on the very high end of the periodic table, have that inherent instability. And for certain isotopes, all it takes is a single neutron, one additional neutron, to overcome the strong force's ability to keep that nucleus together, and you can cause a split to happen. This is called fission. Fission is the splitting of a nucleus into different elements and different component parts. But that fast-moving neutron with enough kinetic energy to get this thing to split up. Now, in this split, not only do you get the products, but you also get additional fast-moving neutrons. And so one neutron in can lead to anywhere from 1 to 3 neutrons out of this reaction. And what can those other neutrons then go and do? The same thing, because you're not going to have a uranium-235 atom just sitting there all by itself. You're not going to have a plutonium-239 atom all by itself. It's going to be part of a bulk. It's going to be part of a bigger structure. And so you get this thing called a chain reaction. Fission events are not singular, they occur in massive groups. Again, depending on how many neutrons you can liberate per fission event and sort of how tightly packed the material happens to be, and if there's any other materials around it. The difference between a chain reaction being controlled and a chain reaction that continues on without any safeguards on it is the difference between a power plant and a bomb. Now, I want to be really clear here. We're going to talk about fission and how it works and how to control it. But the same physics that's going on in a nuclear power plant is what's happening inside of a weapon. But to be exceedingly clear, power plants are designed so that they cannot do a nuclear explosion. It's the same fuel, it's the same material, but the design of the power plant makes it so that it cannot explode with a nuclear force detonation. There just isn't enough material in the correct shape for that to happen inside of a power plant. We are going to talk about Chernobyl today, okay? But that was a steam explosion. It wasn't a nuclear one. All right, so let's talk about the controlled version first, okay? We'll talk about how reactors work, and if you caught the topics that I posted, right, the conceptual question is going to be basically on how do reactors work and all that kind of stuff. So what do we got going on? You need the fuel, okay? The fuel is more than likely uranium-235. That's the majority of fuel that is used in power plants. It's relatively easy to come by. It's easier to come by than plutonium. Plutonium has to be made in a breeder reactor. Plutonium is a synthesized or man-made element, but you need to use a nuclear reactor that is specifically configured for producing plutonium-239. Uranium-235 and plutonium-239 are what we consider weapons-grade radionucleotides. They are isotopes that can fission very easily, and that's what you need in order to be efficient at producing a lot of energy. In that fission event, I forgot to mention, when that neutron comes in and splits that atom apart, there is a lot of energy that's released. Mass gets converted into energy, V equals E equals mc squared. And that's that thermal energy that comes off of that reaction that we're trying to capture. So you have these fuel rods. This is a schematic diagram. This isn't exactly, I'll show you some real pictures here in a second. But you have these fuel rods, and they're big, long stainless steel rods in which pellets of the uranium-235 fuel is inserted. And these fuel rods can get kind of bundled together into a big rod. But they get inserted into the reactor, and then in between the fuel rods come these things called control rods. And control rods, I mean, from the name, what can you guess that they do? They control the rate of the reaction. Remember I said that the difference between a bomb and a nuclear reactor is controlling the rate at which these chain reactions take place. So in a reactor, what you want to do is you want to have the rate going efficiently. If these control rods are inserted in too far, then all of the chain reaction kind of shuts down and nothing's really happening. There's some background heat that gets produced, but essentially the reactor is shut down. If you pull them out too far, then what you have is a lot of excess heat being generated, and that excess heat can start degrading materials, maybe melt down the containment units, all that kind of stuff. And so you want to have this this kind of most efficient way of running the reactor, and it's all about getting the control rods in or out. Control rods consist of materials that act as like neutron sponges they can absorb neutrons that normally would go on and cause a fission to take place, and they'll capture them and slow them down and capture them, so that they can't go on and do any other kinds of fission in the material. So again, think of it like a sponge, okay, and kind of taking those neutrons so that they're not available to go off and split other atoms in the fuel rods. Surrounding all of that is a moderator. The moderator's job is to capture the thermal energy that's being produced in these fission reactions, and then take that thermal energy and move it to a point where it can be used for something. I know the term moderator implies that it moderates or controls the reaction too, and that's partially true. The moderator's job is to kind of take heat away from the system, and so that's a form of control. But really the control rods are all about changing the rate at which the reaction is taking place, capturing those neutrons to prevent them from going off and doing more fission reactions. And then the moderator takes all of that energy that's being produced and is able to bring it to a place where it can be safely used. So I've listed some of the problems on the screen, right? This does generate not a lot of waste. Like, there's more waste that's generated in other processes for producing electrical energy. But the problem is that the waste is really, really nasty stuff. The nuclei that are produced in nuclear fission, these leftover remnants themselves are radioactive, and they tend to have half-lives that are measured in tens of thousands of years. So when it comes to the waste coming out of a nuclear power plant, you have these materials that are going to remain reactive for tens to hundreds of thousands of years. And so dealing with that waste is a problem. In the United States, the policy has been to ignore the problem and do nothing about it. All the waste that is being produced by nuclear power plants, these fuel rods that get spent, all of that waste is stored at the power plants themselves. They go into these things called cooling ponds, where water is used to regulate the temperature of these fuel rods so that they don't melt down, because they can melt down themselves. They can get so hot that they'll turn into molten metal and essentially liquefy themselves. So they're kept in cooling ponds for many years until they're at a state where they're no longer producing so much thermal energy. But they basically have to sit there because the United States has never, ever come up with federal or state policies for the transportation of spent nuclear fuel. We do have ways of transporting nuclear or radioactive materials via trucks and trains to various sites where it can be disposed of. And by disposed of, we basically just put it in concrete caskets and sink those deep into the ground. Again, sort of turning a blind eye to the problem. But as far as like spent fuel rods and things like that, very, very few of those actually leave the reactors where they are used. They get trucked in, but then they never leave. There are other nations, nuclear-equipped nations, that do a better job of this. France is sort of the leading pioneer in how to deal with nuclear waste. France has projects where they're trying to capture some of that excess energy that's coming off of the waste. That's less efficient, but it is energy nonetheless. Researchers in France a decade ago were working on strains of bacteria that seem to like to gobble up spent nuclear fuel and then poop out things that aren't nearly as bad. I know that bacteria don't poop, but you get the idea. France has a policy that they store all of their nuclear waste above ground. The reason being is that they want to be able to continuously inspect the concrete caskets that are used. They call them caskets for a reason. Don't open one because otherwise you're going to need a casket. And so they store them above ground so they can be inspected. France has got it right. As a matter of fact, France is a net importer of nuclear waste. They have very lucrative contracts to take nuclear waste from, say, Japan. Japan doesn't have a lot of place to store stuff, and so they'll pay France a pretty penny to import their waste, and then France will store it, use it for some electricity, energy generation, all that kind of stuff. It's hard to distinguish between a program in a country that is producing these fuels for peaceful purposes, for generating electrical energy, versus taking that material and putting it into weapons. And this is where the crux of the problem comes with nation states like Iran. You probably don't follow nuclear politics the same way I do, but one of the problems and one of the sort of big deals with our relationship with Iran as a country is the fact that they want to enrich uranium. The way that you take uranium-238, which is just dug out of the ground, and you use several different processes, and one of those processes is centrifuges. They literally spin the uranium around, and the different isotopes separate by their masses. And so Iran's been wanting to produce uranium-235 for nuclear power, so they say. The United States and other countries have a different interpretation of that, in that instead of taking the materials and using it for nuclear power, they're instead using it to build bombs. These suspicions are based on things like sort of public statements by Iran's leaders that say we want to wipe certain countries off the map, right? So it's like nuclear proliferation is a big deal, and that's one of the part of the problems here. The same material that can be used to get electricity to the people, to improve their standard of living and all of that, can also be just funneled straight into weapons programs. We'll talk about how easy it is to make a bomb in just a few minutes. Ignore the picture here on the left. Let's concentrate on the picture on the right. What you are looking at is a nuclear reactor with its lid taken off. Normally there's a lid on top of here. This picture on the right is a picture of what we refer to as a research reactor. So this isn't one that is being used to produce electrical energy. It's being used to determine like reactor geometries and the best shape to have your fuel rods and all that kind of stuff. If you look closely, you can see some white, very, very bright white circles down there. Those are cavities that they have removed, either control or fuel rods, out of this reactor. That blue glow is real. I've seen it. It's a form of radiation called Cherenkov or Cherenkov. I can never remember his name, radiation. What you are seeing is it's like a sonic boom, but for light. So the speed of light goes down when light travels through a material other than the vacuum of space or air. In water, the speed of light is like half that it would be in air. And so what happens is if you get radioactive particles, alpha, beta, gamma, moving through the water faster than light can travel through the water, you end up forming a type of it's not a sonic boom, it's not sound waves that are doing it, it's light waves that are doing it. And that radiation of those light sonic booms is that blue glow that you see there. It's not impossible to move faster than the speed of light in a material. You can't move faster than the speed of light in a vacuum. But if light slows down in material and you've got something that moves faster through that material, that's not breaking any of the laws of physics. And what we're seeing is a visual representation of what happens to the amount of energy that comes out of something when a material moves faster than the speed of light in that material. That's that blue glow. The other sort of things you see going down into the core of that reactor there are instrumentation. So these are ways that they use to monitor what's going on in the reactor and all that kind of stuff. In this reactor, the moderator is water. And that is true for all of the nuclear power plants in existence in the United States. We exclusively use water as a moderator in our designs. The picture on the left, here is a picture of what a commercial power-producing reactor looks like when its lid has been taken off. Again, we'll get to why there's a lid in the first place, right? But again, you see that blue glow that's happening. And then what they're doing here is they're using like crane attachments. They come down and they pull out these huge, big, long boxes, okay? They're about, I don't know, they're about like 8 inches on a side, but then they're many feet long, okay? And inside of those, they'll have collections of both control rods and fuel rods. And so what they're doing is they're going in and replacing fuel rods with new fuel rods and checking the control rods to make sure that they can still absorb neutrons.
How do you know when the fuel rods are like done?
Your reaction starts lagging behind and not being as efficient.
Oh.
I'm glossing over a lot of the engineering behind how you tell when a reaction is happening correctly. But there's kind of a balance point that they're trying to achieve with the reactor. And at that balance point, you're like, you've got an amount of energy that's coming out per time, like a rate of energy that's coming out of your reactor, while simultaneously you're not using fuel at a fast rate. It's kind of like the nuclear equivalent of driving your car. You get your car up to speed, and then you can kind of back off just a little bit. And you know how your car has different gears that it'll get into to run the engine at a lower RPM but keep the speed? It's nothing like that in a nuclear reactor, but that's kind of like what it is, okay? They don't have a transmission, they don't have gears, right? Yeah. But they have ways of tuning the reactor output so that they're using less fuel but still getting the same amount of energy out, that kind of idea. That was mostly a lie, but it's a good lie. Because the nuclear engineering is actually pretty complicated, and I don't understand half of it, right? When nuclear engineers talk, I'm like, okay, now you guys are just doing black magic, right? Because what you just sounded like broke the laws of physics. And they go, oh, no, this is how it works. And you go, okay, fine, whatever. So anyway, this is what a commercial reactor would look like. Much bigger core, right? And this crane thing comes down, picks stuff out, and then that leaves, and then they put the lid back on so that they can ramp up the pressure. The picture on the left-hand side is a picture of the very top of the world's first fission reactor. This reactor was built in the United States during the Manhattan Project. As the Manhattan Project ramped up, the Manhattan Project was the project to produce the world's first atomic weapons. And about a third of the way into the project, this is about 1943, a scientist by the name of Enrico Fermi, he was an Italian scientist, he was Jewish, he fled the rise of fascism in Italy under Mussolini and came to the United States. He would go on to win a Nobel Prize, but he was kind of selected out of the Manhattan Project to lead the what would become the projects that would happen after the Manhattan Projects that would produce the world's first nuclear reactors that were producing electricity. So these sort of, when peace happens, when the World War is done, what do we do with this science? What do we do with this technology that we're developing to make weapons? So Fermi was tasked with doing that. And this picture right here, okay, is the top of Fermi's first reactor. I don't know if you can see it, but do you see how it's made of like little tiny bricks? Okay, so that's the only picture we have of the reactor. So Fermi came to the United States, got a position at the University of Illinois at Chicago, and he was teaching, he was doing research, but he was also a part of the Manhattan Project. And so he's tasked with this ultra top secret project, right? A spin-off of the Manhattan Project. And he's looking for a place that he can, in secret, build the world's first nuclear power reactor. The Manhattan Project decided to set up shop in the middle of nowhere, New Mexico. There's nothing more top secret, right, than overnight near Santa Fe, Los Alamos, right? Overnight, it goes from like sagebrush and bunnies and rattlesnakes to 5,000 people, right? A town of 5,000 people materializes almost overnight, and the vast majority of these people are mathematicians and physicists. That's not weird at all, right? Never mind that the town's got barbed wire all around it and nobody's allowed in or out and all, right? Nothing crazy going on here. Fermi took a kind of a different page, right? And he decided to hide his reactor in the one place that kind of made sense to him. There was an abandoned racquetball court underneath the stadium at the University of Illinois in Chicago. They called it squash ball at the time, but it was a racquetball court. Okay, it was in like the third basement of the stadium. And nobody was using it, and so he asked the university, hey, can I do some physics experiments in there? And the university was like, sure. Okay, and so that's where the world's first nuclear reactor was built. in a racquetball court on the third sub-basement of the football stadium at University of Illinois, Chicago. Now, again, to be clear, nobody was going to get blown up, right? There wasn't enough material in this reactor to create a bomb. And but again, there was radiation. And Fermi's reactor, this is an artist's impression of it because most of the pictures were destroyed as an effort to keep it top secret. You can see here that it's a literal pile of bricks, okay? And so the moderator in Fermi's reactor wasn't water, it was carbon bricks. It's exactly what charcoal, right? Charcoal bricks, okay? Graphite is what it was. And so they had to ship in like multiple tens of tons of graphite bricks to the university. And so they had to like ship it to different parts of Illinois to make it not look suspicious that it was all coming to the football stadium, right? And they affectionately called their reactor the Pile because it was literally a pile of bricks, okay? Just lots and lots of graphite bricks in which they manually inserted fuel rods and then manually pushed control rods in and out of the reactor. You can see down here is the artist's interpretation of Fermi standing there, kind of moving the control rods in and out in an attempt to get the reactor to sustain its fission reactions. It's actually fairly easy to do something called poisoning a reactor, where if your control rods get inserted too far, it like completely shuts down the fission process, and you have to kind of go through this complicated restart process to get it to happen. You can be producing like certain noble gases like xenon and other things that can kind of get in the way of of the nuclear processes that are going on. And so it was a balancing act, right, to get this thing to work. This is, again, an artist's interpretation of the day that they first sustained a fission reaction within the pile. And about 10 days before this was to take place, the United States finally told its allies, Great Britain and others, that they were working on this project. The British were not happy about this, that it had been kept hidden even from them. But they were grateful to be able to come and see the first attempt. There was a coded signal that was sent from the observers that were looking at this going on, okay? And the coded signal that was sent to President Roosevelt said that the Italian navigator has landed in the New World and has found the natives friendly. Who was the Italian navigator? Enrico Fermi, right? What was the New World? Nuclear power, right? And the natives being friendly? It didn't blow up. It worked, okay? It wasn't going to blow up, but finding the natives friendly meant that the project had worked. It never produced electrical power. It was a proof of concept. It was a lab project, right? So to get the electrical power part going, you basically have to bolt a power plant on to the reactor. Most electrical power plants, so not talking about wind, solar, or hydro, because those are all different, right? But every other power plant uses exactly the same principle to generate electrical power. They all boil water. Whether it's oil, whether it's coal, whether it's natural gas or nuclear power, all four of those generate electricity exactly the same way. Use the fuel to boil water, and once you boil the water, you can use that steam to turn a turbine, which creates the electrical power. So in essence, power plants are just coffee makers, right? What does your coffee maker do? It boils water, right? Really fast, okay? And shoves that boiling water and steam through the coffee grounds to produce your coffee. The difference between a nuclear power plant and all the other power plants is how you generate the heat to boil the water, okay? In oil, gas, and coal, you can basically it's like your stove. You just dump a bunch of heat into water, right? Boil the water, you're done. In a nuclear power plant, you're using these fission events, okay, which are producing radioactive materials, radioactive neutrons, all that kind of stuff. So the moderator in the United States that we use, water, is radioactive, but it stays closed. It stays inside of a closed system, and we use something called a heat exchanger in order to move the thermal energy around. So the moderator water, which is highly radioactive because it's in direct contact with all of these fission materials and the materials that are produced after fission and all that kind of stuff, that boiling water that's in the reactor gets circulated by a water pump. More on those water pumps in a second. That hot water gets moved into something called a heat exchanger, again, where the water doesn't mix, but thermally, energy can move from the hot water into another source, vat of water, tank of water, and it's that tank of water that produces the steam in order to generate the electrical energy. It's really important to understand that there's this closed system inside of a nuclear reactor, and this is how nuclear reactors, this is their superpower, which is also their Achilles heel. The nuclear stuff stays inside. It's in a closed system. You got to top up the water every once in a while, but you don't need to get anything out. The heat that is generated gets done so in a way that produces steam and water that is not radioactive at all. And so when you see discharge coming out of a power plant, it's just hot water that's flowing out of the power plant. It's not radioactive water in any way, shape, or form. But again, the Achilles heel part comes down to these pumps. If these pumps stop, if the moderator pump fails, then you can no longer move water through the core and keep its temperature down to safe levels. If the water pumps fail inside of the heat exchanger, then again, you're unable to get the thermal energy out of the reactor fast enough to keep the reactor from melting down. So every nuclear reactor is of a size and configuration where meltdowns are completely possible. If you lose the ability to put the control rods into the reactor, big problem because you can't slow it down. But even with the control rods fully inserted, reactor designs out of the 1960s and 70s were such that you had to maintain the moderator and heat exchanger flow. If you couldn't keep that flow up and the water stopped moving, it would heat up enough to cause the materials in the reactors to begin to melt. They would get so hot, they would turn into liquids, and they would begin flowing, and they wouldn't cool themselves off because the nuclear reactions would continue and continuously heat it up. This was colloquially known as a meltdown, but internally known as the China syndrome. Because once you had a core that was in meltdown and it was starting to flow, there was no way to get control rods in there, no way to get the moderator to get the heat off. That molten puddle of fission material, okay, would start following gravity, okay, and just start melting through any material it found because it's hotter than lava, okay, and it's starting to go through. And China syndrome was coined because where was it going to end up? Digging a hole to China, right? Because China's on the opposite side of the planet from the United States, okay, which is not technically true, but culturally we were jerks and kind of still are, right? So that's where that term came to be known as China syndrome.
The images you showed us earlier for the top view,
Yeah.
is that the reactor area?
Yeah, it's taking the lid off the reactor on this side. Yeah. So inside of that reactor vessel, it's a pressure vessel. It's a pressure cooker. If you've ever used a pressure cooker like an Instapot or something like that, right? You can keep water in its liquid phase and get a lot of thermal energy into it, right? By keeping the pressure high. And that's exactly what happens in a nuclear reactor and really any one of these boilers that's taking place. You then exchange that heat in the heat exchanger to turn the turbine, turn the generator to get the electrical power. But again, key, very important thing to have running at all times are these water pumps. If the water pumps shut down, you're in a world of hurt when it comes to designs that were designed before the early 2000s. This is a picture, I think it's, reactor number 4? I get the reactor numbers mixed up with Fukushima now, but that one's happened. But this is Chernobyl. This is outside the town of Pripyat in the former United Soviet Socialist Republics. It is now Ukraine, or located in Ukraine. It's actually located currently in contested territory inside of Ukraine. But this is a picture of the roof of the reactor vessel. And it can be difficult to see, but there was a fire that burned out a lot of this. But what happened at Chernobyl was a runaway reaction in the core that subsequently caused a steam explosion. So the explosion and subsequent fire that happened at Chernobyl wasn't a nuclear explosion. It was a steam explosion. Too much steam built up into the reactor and caused an explosion to happen. It's, again, hard to see in the picture, but there's sort of an arc, kind of a high contrast. You can see it down inside of this kind of dark area right there. There's a little curved part. That's the lid of the reactor, okay? That was blown off and subsequently fell back down and is at a weird angle. I don't have time to go into everything that was happening that led up to this disaster. Suffice it to say, and I've studied this a lot, and I've been fortunate enough to meet with people who were assigned to go and investigate the Chernobyl incident. This explosion was not an engineering mistake. Suffice it to say, the short version is it was a political mistake. It was the mistake of a government that was unable to effectively feed its people, let alone get the correct materials and training to people who were responsible for running these reactors. The engineers running the reactor that night were under orders to conduct tests that they knew was going to put the reactor into dangerous modes, dangerous operating states. What they failed to recognize at the time is what was happening inside the reactor. Their instruments were saying one thing, but a very different thing was going on inside of the reactor. Again, due to lack of training and pressure from the central government to get certain tests done on these reactor designs. The Soviet designs used graphite bricks for their moderators. There was water also present, but the majority of the moderator was graphite bricks. And at approximately 1 o'clock in the morning, a large explosion was heard coming from the direction of the power plant. And emergency crews responded, firefighters responded. And as they pulled up, the firefighters would later recall that they thought it weird that they saw a bunch of bricks all over the ground. The building was made of reinforced concrete and rebar and steel, right? And so it shouldn't have been made of bricks at all, and they kept wondering what these bricks were doing all over the place. What were they looking at? They were looking at the graphite bricks that were part of the central core of the reactor. When that reactor heated up, it turned all of the water in there to steam really, really fast, and then that steam exploded, causing the fire, sending the radioactive fuel rods, control rods, all over the place. It released a cloud of radioactive steam that immediately drenched the surrounding area and would later move all over the world. The amount of devastation was enormous and is enormous because it continues to this day. Sim, you had your hand up.
How far deep did it penetrate into the ground?
It made it all the way to the lowest basement before it stopped.
But nothing below that.
Nothing below that. Okay.
So if it built higher, you think the steam would have just let off and not caused a fire?
No. No. Okay. So what you're looking at is that basement area that the flow finally made it to. Okay. This is a huge place where water comes in. To give you an idea of scale here, so the person taking this picture has to be bent over in the space. But these flanges right here are about they're about 18 inches or so big. Okay, big water connections, right? Do you see the, like spaghetti-like or hair-like material that's kind of coming out here? What that is solidified graphite and nuclear material and control rod material as it had flowed down through the plumbing, okay, and started burning through stuff, right? It finally flowed out, okay, and eventually got to a point where it could cool off enough so that it didn't keep melting. So Chernobyl was a complete meltdown. Chernobyl was a steam explosion. Okay? Chernobyl is the worst radiological disaster that we have ever seen or contemplated as a race. This map shows the extent to which radiation was sent all over Europe and Asia. The black box is the location of the power plant, and then the different colors are trying to indicate the level of contamination. You can see here, right, that the contamination not only moved from west to east, but it also kind of circled back and ended up in places like the United Kingdom, especially up there in Scotland, for a period, I remember, so it was 1986 when this happened, and I was 12 years old at the time. You guys can do the math. And I remember there being like import controls on Scottish sheep meat. There was a period of about 20 or 25 years in the UK where it was illegal to slaughter sheep from Scotland for consumption purposes. And the reason is that because the sheep meat was too radioactive as a direct result from the Chernobyl contamination. You could still do their fleece, you could still do their wool, all that kind of stuff. It's just you couldn't sell the sheep meat as mutton. It just had to be destroyed. Similar things were happening in other parts of the world. Ironically, China recorded one of the best grape harvests of all time from the radiation they received, and it's still known as the Chernobyl vintage. The 1986-1987 harvest. But the amount of radiation that got spread all over the place was small. It was very highly concentrated in the immediate area around the power plant. There's an exclusion zone that was set up around Chernobyl. It was a 50-kilometer radius exclusion zone. Everybody living inside of that area had to be removed, okay, forcibly moved. Some people refused, other people came back later. We might talk about them. But in the town of Pripyat, which was a kind of a new town, it was built up to be the place where all the engineers and their families would live, right, who were running the power plants along the Pripyat River. They were evacuated overnight. They were told that they would return in a few days, but they had to get out, and they never came back. And the town became like a ghost town, like a weird time capsule where toys and dinner plates were still on the tables, and like nobody took their pets, and so the dogs became feral dogs and the cats became feral cats. Like, it's just this kind of weird, very strange, and you get an idea of where like science fiction gets some of its dystopian ideas from, right? Because all they have to do is look at the exclusion zone around Chernobyl, and you've got a case study for it. To contain the radiation that was impossible for them to clean up. Initially, the Soviet government took the army and had the army start like shoveling dirt over the top of the reactor, and they would hand a soldier a shovel and say, run up to the edge, shovel for 1 minute, come back and wait 2 hours.
Oh my God.
Just to try and keep their radiation exposure down. The firefighters, the first responders that went in, their clothing was so radioactive. They were getting the initial signs of radiation sickness almost right away. And they were brought to the Pripyat hospital, and the doctors couldn't figure out what was going on until somebody grabbed a radiation counter and then realized that their clothes were saturated with radioactive particles. And the room that they took the firefighters' clothing and they stripped it off their bodies and just chucked it into a closet. That closet is still one of the most radioactive places in the town of Pripyat to this day. I believe it was 28 people died in the explosion and then subsequent efforts to contain the radiation. There would be many thousands of people that would have long-term effects from the radiation. And the total death toll is kind of hard to pin down. But around 30 people would lose their lives. So the Soviet government commissioned a sarcophagus. These terms are used intentionally, by the way, in the nuclear industry. These are not derogatory. These are what nuclear physicists use to describe the kinds of things that you need. Okay? It is all dark, and it's all terms relating to death for reasons, right? So this sarcophagus was built around the reactor. It was a steel and concrete structure that was designed to contain the radioactive materials that were in there because it was too dangerous to go in and dig those materials out and dispose of them correctly. They were just all over the place, and it was too mixed up, and it was too hot, and nothing could survive, all that kind of stuff. This sarcophagus, I think, was completed within like 3 years of the incident. Everything you see in this picture and more, every crane, every tractor, every pipe, every tool taken into the exclusion zone to work on this, to build this, had to stay. because the tractors were becoming radioactive. The metal of the tractors were becoming radioactive, and therefore had to stay within the exclusion zone because they were too radioactive to be used anywhere else. Engineers and civil engineers would scrape the top meter of soil up from huge areas in the towns and surrounding the reactor and pile them up into mounds of dirt and cover those with concrete because, again, the dirt was radioactive. There was radiation everywhere, and the cleanup effort continues to this day. The nature of the red parts here are, you can see where the molten material finally made it to, okay? And all of just the incredible mass. And so the sarcophagus was designed to kind of contain all of this, realizing that it's going to be about 50 or 60,000 years before the insides of this thing reach a radiation level that will be safe to deal with, assuming our current level of technology is what we'll have in 60,000 years. Ideally, we'll have something better at that point to deal with this stuff. But at current levels of technology, it'll be 60,000 years before we can safely begin cleaning up the reactor and its core material. NASA volunteered the use of some of its prototype Mars rovers to help inspect what was going on inside of the sarcophagus after several years. These probes, you have to understand, are designed to live in the radiation of interplanetary space. Between planets, there's no magnetic shield to protect electronics from the full force radiation of the sun. And so these rovers are hardened and designed to live, to just cruise for 6 to 8 months between the Earth and Mars, being constantly bombarded by alpha, beta, gamma radiation, right? And so these probes can withstand high radiation environments. They lasted for about 20 minutes inside the sarcophagus. And in that 20 minutes discovered that the 1 meter thick walls, concrete and rebar, had decayed to a point where in some places they were only 10 centimeters thick. Just this constant radiation bombardment of these materials were weakening them and crumbling them. So they had to build a second sarcophagus, which was started in 2013. This one is the largest movable man-made structure on the planet. It was designed like a kind of a bridge and truss system, and it sits on rails. And what this allows is this sarcophagus was built off to the side and then rolled over the top of the reactor and its original sarcophagus. There it is in 2013. Okay, March 2016. You can see the reactor with the old sarcophagus right here, and they're building this structure in the foreground off to the side. And then they moved it and rolled it over the top and kind of sealed it off. But inside this sarcophagus are cranes and other machinery that will begin to kind of disassemble the reactor and get to parts that aren't as bad and try to start cleaning those up. So this building, right, finally made it over the reactor in the winter of 2018, okay, and has been serving ever since as a containment unit for the cleanup that is going on in there. This structure is designed to be like maintained and rebuilt sort of more or less constantly. And there is a 100-year plan in place for having that happen. Now, that 100-year plan got disrupted approximately 4 years ago when Russia invaded Ukraine. And no work has been taking place on this structure since. So that is of concern to us physicists that keep track of nuclear power and its power plants and everything that's going on. This is a coffee shop in the town of Pripyat. Pripyat, as you can see, they've had lovely roses. It was Cold War design, build everything as a cube, right, out of concrete in case the bombs fall kind of thing. But Pripyat was like a modern Soviet town. It was not too different from like Fresno, right? In the amenities that it had and all that kind of stuff. It was smaller. It was, I think it had at most 50, 60,000 people that ever lived in it, right? So smaller than Fresno, but not too different. Rural around the outside, lots of farming going on, all that kind of stuff, right? So here's that same cafe 10 years later, right? With humans gone, right? Nature is beginning to take over. Materials are degrading. Here it is 10 years after that. You can see the incredible growth that's taken place. The exclusion zone around Chernobyl has become a kind of a scientific paradise. And if there is a silver lining to any of this, and I'm not saying any of this is good, but if we're going to make lemonade out of the lemons we've been given here, the amount of research that's been able to be done on like biological systems in high radiation environments is incredible. The rate at which nature has managed to reclaim the town of Pripyat has far exceeded biologists' estimations. Like, long time it was assumed that the impact of humans on planet Earth was going to be measured in like if you took all the humans away, it was going to be thousands of years before it all degraded. Those are all updated now to be like 10 years, right? Like nature. So I don't have pictures of it, but like the soccer field in Pripyat, right? They couldn't find the soccer stadium. What they did find was a huge new forest that had grown up in the stadium, and they were walking through the forest and they got about 10 feet away before they realized that they were about to run into the bleachers, because the trees had grown through the bleachers and like lifted the bleachers up and sort of moved them along. And like trees, like it's always assumed that trees couldn't colonize like pavement, like the concrete and asphalt. No, there's some forests in Pripyat that are eerily straight and rectangular in shape, because the trees just grew in the pavement and then tore the pavement up. And you've got this kind of weirdly rectangular forest. So nature will always find a way. Wolves, gray wolves that were thought to be extinct in that part of the Ural Mountains, reintroduced populations into the exclusion zone. Reason being, the humans were gone, right? And they had a safe haven. Of course, very high rates of mutations among everything. Insects, fish, frogs, deer. It's hard to keep track of like mutations and stillbirths and all that kind of stuff because nature recycles that stuff too fast. But the populations of wolves, deer, insects, birds, everything, plants, fungus that lives inside the exclusion zone has evolved to live in that high radiation environment and has specific evolutionary traits responding to it. So it's a wonderful scientific opportunity to see what happens not only in a high radiation environment, but also what happens when you remove humans from an ecosystem. Now, humans have been moving back. There are people that actually live in Pripyat now on a full-time basis. They've cleaned up a lot of, there's still, you don't want to step off the road really. And before the war in Ukraine, you could schedule tours through the town. There were vacation packages. You could go and get a tour through the exclusion zone. People will spend money on anything apparently. But yeah. All right, what you're looking at here is Fukushima Daiichi, a nuclear power plant on the coast of Japan. And I'm not going to remember the exact dates. It was circa 2010. But a magnitude 9.3 earthquake struck off the coast of Japan, Japan's eastern coast, which is where Fukushima Daiichi was located. And that earthquake caused the entire eastern seaboard of the main island of Japan to drop 1 meter in elevation. The amount of energy that's required to cause a change of that magnitude is enormous. We're talking tens of thousands of nuclear bomb type energy in a single earthquake event. In the shifting of the tectonic plates that took place, water was disturbed and a column of water got pushed up. And the resulting tsunami as it came into the Japanese coast was approximately 15 meters high. So 15 meters is about 45 to 50 feet. Okay? Wall of water moving towards a coast. Now, if there is a people that is most like prepared for earthquakes and tsunamis, it has to be the Japanese. They are the world leaders in disaster preparedness because their entire nation is built on an island chain that is still forming. Okay? Volcanoes, earthquakes, the Japanese lead the way. And in Tokyo, this huge, largest metropolitan city in the world, right? I don't think there were any deaths directly related to the earthquake, like falling debris or any of that kind of stuff. In 2005-ish, there was a tsunami that struck Indonesia. And that tsunami killed about 250,000 people. 240,000 people lost their lives in that tsunami. And I think it was only like a 3 or 4 meter high tsunami. In Japan, only about 10,000 people lost their lives as a result of the earthquake and tsunami. And the tsunami was much bigger. The Japanese people drill all the time. How do you escape from a tsunami? What do you do in an earthquake? They are the world leaders in this. And so they cannot be faulted for what happened at Fukushima Daiichi. This is a satellite aerial reconnaissance view of the power plant from Google Maps. You can see the reactors, and then you can see this like sort of a harbor where the ships would come in to deliver the fuel and take the waste away. And you can see the seawall that's there. That seawall was designed to withstand a 15-meter high tsunami. That was in the planning. It should have been able to take care of it, no problem. And a 15-meter high tsunami was on its way. What they didn't account for was the fact that the entire eastern seaboard had dropped by 1 meter. And so this tsunami overtopped the defenses and flooded the power plant. Remember those turbines? Those motors that have to keep the cooling water going? Okay. When the earthquake hit, all of the power plants, nuclear power plants, all over Japan went into their safe modes the way they are supposed to. In fact, they started tripping before the seismic waves arrived because of the warning system that they had. And so within like a second or two before the actual earthquake hit, these reactors were already responding and shutting down. And it takes approximately 5 to 10 seconds for a reactor to go into full shutdown mode. And the inertia in the system can keep the water flowing for about 45 seconds to a minute. And that's time where if you lose power to run the pumps, you need to get some backup power. Well, all the backup power is run by diesel electric generators. Diesel electric generators are known far and wide to be one of the most robust systems for providing electricity to hospitals and other critical infrastructure when the rest of the power grid goes down. So the diesel electric generators kicked in and started running those pumps to just keep water moving. They're not generating electricity. The reactor's in full shutdown mode. They're just keeping the cooling water going. The problem was that those generators had been installed in the basement. And that basement flooded because of the tsunami. The tsunami would rush for several kilometers inland, just destroying homes and farmland and all kinds of things. And it would inundate the diesel electric generators, which would stop running, which meant the cooling water would stop flowing, which meant that heat would build up inside of the reactors. I remember watching the news coverage of this, and I remember watching this explosion in real time. Like they had the news anchor was sitting there and the Fukushima Daiichi was behind them. and the explosion happened, and the dust cloud started to rise, and of course, the anchor freaked out, and the camera crew the cameraman, praise the cameraman, was just like locked on, okay? I love that Reddit, right? Like, that is just like, the cameraman was like steely. Maybe he was running the other way and the camera was just locked off, I don't know. But they started talking about, there's been a nuclear explosion, and I was like, how do you know this isn't a nuclear explosion? Because they're still there. Okay? This is a hydrogen explosion is what this is. Okay? So the explosion, do you see that conflagration that's sitting right there? You don't get fire like that in a nuclear explosion. Okay? You get a bright flash of light and you're done. Okay? This is a conventional explosion. This isn't a steam explosion. What this is a buildup of hydrogen. Remember, water, right, is the main moderator. And under high bombardment from nuclear materials without cooling, that water can begin to dissociate into hydrogen and oxygen. And now you got hydrogen gas with oxygen gas and a source of heat. What's going to happen? Boom. So this wasn't the reactor letting go. This was gases that were building up in the systems starting to go. And the hydrogen would leak out and it would get into the spaces around it and it would blow up. The Japanese did amazing work in keeping these reactors cool to the point where they knew they were going to lose the reactors, and so they started injecting salt water in as an attempt at that. That's a death sentence for any nuclear reactor. And then that wasn't working, and so the firefighters started pumping water from the ocean and just spraying it onto the buildings in order to keep it cool. And they did. They managed to keep it cool enough so that any meltdown that occurred was completely contained within the reactor core itself. Fukushima Daiichi is going to require about 50 years to clean up. And the cleanup has begun. Okay? They're filtering things. There's a whole bunch of neat engineering that's gone into it. But it is nowhere near the level of disaster that Chernobyl represents. Chernobyl, we've got tens of thousands of years before that place is going to be safe. Fukushima Daiichi is going to be safe in about 50 years of continuous work. It's a big expense and it's a big problem, but it's certainly within the realm of being solved. Very quickly, let's talk about how you make a bomb. It's really simple, and I'm not giving away any secrets here by teaching this. I remember after 9/11, I got a bunch of calls from concerned community members who charitably, I will say, were well-meaning, and they said, of course, you're not going to be teaching that nuclear stuff anymore, right? And I was like, no, why? Well, what about bombs? I was like, okay, to make a bomb's really easy. And this is not something they wanted to hear, right? The actual engineering of a bomb is actually fairly complicated, okay? But the physics behind making the bomb, drop dead simple. What you need is you need enough material so that the neutrons can't escape from the surface fast enough so that the chain reaction just continues. It's called a critical mass. And so here's how you make a bomb. Take two subcritical pieces of, say, uranium-235, right? And then just put them together. The instant you put them together into a critical mass, it will explode in a nuclear detonation, because the chain reaction will go so fast that it cannot stop. And that's exactly what the United States did. The bomb that was dropped on Nagasaki, the second bomb, was of this design, where a subcritical piece of uranium-235 and another subcritical piece of uranium-235 were separated at either end of the bomb casing. They put an artillery gun barrel inside, and they shot a subcritical piece of uranium into another subcritical piece of uranium that then underwent a fission reaction. A radio altimeter was installed in the nose of the bomb. When it got 1,000 feet above the ground, the charge went off. The gunpowder charge shot that piece of uranium in, and then the nuclear fission reaction went off. The bomb that was dropped on Hiroshima was of a slightly different design, but same idea. What you are looking at is a picture of a nuclear test that took place in Nevada, but similar pictures were made of the very first tests that were done in August of 1945 out in the deserts of New Mexico. The amount of energy released in a nuclear explosion is hard to quantify, but we're going to make an attempt, okay? This little tiny mushroom cloud down here, okay, represents the largest conventional explosives we have in the U.S. arsenal, the so-called bunker buster bombs. These are very large yield conventional bombs that are designed to penetrate down into concrete and rock and mountains and that kind of stuff and then go off, okay? A bomb's yield is measured in tons of material, tons of TNT. So you might hear about like a 500-pound bomb or a 1,000-pound bomb. That's not the actual weight of the bomb hanging from the airplane's wings. It's the yield. It would be as if you set off 500 pounds of TNT. And a stick of dynamite's about 2 pounds of TNT. So that's kind of how you rate an explosive. Well, the bunker buster is measured in like tens of thousands of pounds of explosive yield. The bombs dropped on Hiroshima and Nagasaki were estimated yield of 15 kilotons TNT. So what's a ton of TNT in the U.S. system? How much is in a ton? How many pounds? 2,000 pounds in 1 ton. And then the bombs that went off on Japan were 15,000 tons of explosive yield. The bombs that were tested at the Trinity site in White Sands, New Mexico had estimate yields of about 20 kilotons, 20,000 tons of TNT. The explosion at the test site was so large and so energetic that it fused the surface of the desert into glass. Glass is mostly silica, sand. And the surface of the desert, to a radius of about 1 mile around, was fused to a depth of 3 inches into glass. Like, that's how much heat was generated. You can still go out there and the little gift shops will sell you pieces of trinitite. That's what it's called. This glass that was made by the explosion. But these fission explosions are dwarfed. So these are fission. This is splitting the atom type explosions, okay? They are dwarfed. There they are to scale to the 3 largest atomic weapons that have ever been tested in humanity's history. Measured in megaton yield, these are fusion weapons. Fusion is an orders of magnitude higher than fission. But instead of splitting atoms, what you are doing is you're bringing atoms together. And in that bringing together of nuclei to form new nuclei, a lot more energy is released. Fusion has enormous destructive capability, but also is the future of what we are going to be doing when it comes to producing electrical power. When fusion works, not if, but when fusion works, it will be a source of very clean, but not perfectly clean, electrical energy. The thing about nuclear energy right now is it is the only carbon neutral source of energy that runs 24/7. Solar doesn't run 24/7. Wind doesn't run 24/7. And hydroelectric, there isn't enough of it. It can run 24/7, but there just isn't enough of it to satisfy energy needs. So nuclear is always going to be a part of our energy makeup because we don't have any way to store energy. We're coming up with ideas of storing energy, but we're not getting quite there yet. California's managed to run, like for more than 100 days last year, we ran on completely renewable energy. Being able to store excess energy during the day and dump that back into the grid at night. So it's happening. The energy revolution is happening. But if we can get to fusion, well, that's going to be something else entirely. So this is $3.50 a gallon. I can't remember what gas prices are right now. What are they? I drive an electric car, so I have no idea. About $4 a gallon. So this isn't far off, right? Okay. So take a look at this, right? In gasoline at $3.50 a gallon, you get about 10 to the 8 joules of energy out. Okay. Seawater containing 0.12 grams of deuterium, which is the chief fuel of a fusion reactor, okay, costs about 4 cents a gallon, right? And produces more energy. The key is unlocking it, right? And to unlock it is going to require quite a bit of really good engineering. And projects are underway right now. There's several startups as well as international projects. These are different pictures throughout the years, but this is the picture of ITER, which is a huge test reactor that's going in France. Here you can see them installing the big D-rings and all that kind of stuff. It's a huge facility. It's not designed to produce energy for the grid. It's designed as a sort of proof of concept, and will point the way towards power plants that will actually be able to do it. Fusion is one of those things that's always seemed to be about 20 to 30 years away, and it's still 20 to 30 years away, right? But it seems like every couple of years we're chipping away at the significant engineering problems that need to be overcome to make it work. This physicist is cautiously optimistic that by 2100, fusion will be our primary source of electrical energy generation.
Will they have to use the same like water cooling system?
Nope.
No?
There's one thing you need to know about fusion. It is not entirely clean. There are radioactive byproducts to fusion. Fusion, you put together a couple hydrogen atoms, you get helium. So we're going to solve the party balloon problem. Okay? There's going to be plenty of helium once we got fusion going. However, there are neutrons that are produced in that reaction, and those neutrons can go and embed themselves in the material of the reactor. The good news is you can run the reactor for about 40 or 50 years before it gets to a point where it's so radioactive you have to shut it down. And even then, the half-lives of those materials are measured in years. So the cleanup and the subsequent how long does the radioactive waste last, it lasts within years, not tens of thousands of years. So it is radioactive, there are byproducts, but they are a lot less than the fission reactions we have going today. I want you to have a great Thanksgiving. Okay? Be safe. Come back to me in one piece, and I'll see you on the other side. Next Monday is just grasp. I will not be presenting anything. You just come in for help or to turn stuff in. I'll be there all day. You can come when you want and get your homework done or whatever. Next Tuesday is review.